Hey folks, how's life going? I'm asking you despite the fact that clearly you can't answer. It's easier to ask people about themselves that way when you know they can't answer. Less tedious. All right, so enough jokes. So let's see. Today we're going to cover the second, third, or even a little more than that of complexity theory as a lecture, which will include connectedness, tipping points, and early warning signs, which are early warning signs of tipping points. So we'll see. I'm going to go for not a duration, but a specific amount of content that I mean to address. A couple of things. You guys are probably working on your questions today because you have to have them to be by tomorrow morning. I get up at like 5 a.m. So like you could submit them at 2 a.m. tonight. I'm not going to see them until tomorrow. But I'm going to compose the exam tomorrow, so please have them to me by tomorrow morning when I wake up so that I can make this exam, because I want to make sure that it has as few mistakes as possible before giving it to you. Make sense? All right. Other things, the exam, I'll try to have it available at 11 a.m. I'll have it available all day long. If you have a special accommodation, you'll have additional time based on that requirement. So if you have special accommodations, I'll allow the exam to be taken until Sunday. So anything else? The exam will be between 40 and 45 questions, which means since there's 60 of you, it means the average individual is going to have one or not one of their questions taken for the lifted for the exam. So please do not be shocked if your questions don't get used. Just creating the question is a great way to study, but I cannot compose the exams exclusively of these questions. And so I'm sorry if I did not use one of your questions on the exam. And if you produce 5 fabulous questions, I'm also sorry because I'm only going to use like 1. If I use 2, it's an enormous compliment. Okay, like maybe. I mean it to be. It must be very good in those conditions. Okay, so connectedness. So we talked about a lot of different features about complex systems up until this moment, but connectedness is just the idea that one complex system studied in isolation, while useful, thinking about its feedback loops and its dynamics and its nonlinearities and how it organizes, what maintains it, what gives it different qualitative stable states that it can exist in. That's nice, but oftentimes the way we approach complex systems, I study the human brain, I study kelp forests, I'm studying aridification of Africa, I'm trying to study meerkat societies. Well, the reality is that oftentimes we have a hard time understanding the behavior of our focal complex system because it is coupled, i.e. connected, to another complex system. So in addition to having these various nonlinearities and feedback loops that describe your system, oftentimes another system is tied to it that is obvious sometimes when you think about it, but traditional disciplinary boundaries prevent individuals from thinking about those feedbacks between multiple complex systems. The outcome of what's happening here invariably will feed into the parameters of this other system, i.e. the environmental features that govern its behavior. So connectedness, yes, complex systems are usually coupled to other complex systems because they exist in the same reality, right? And so systems can be connected either vertically in terms of tiers of organization or laterally in terms of tiers of organization. So a tier of organization might be like ecosystems, communities, an individual organism, a social group, or even an organ. Even a cell itself is a complex system that has all of those features. So laterally would mean that there are 2 systems connected to each other and the 2 systems are on comparable levels of organization, tiers of organization. T-I-E-R-S, not T-E-A-R-S, so tiers of organization. And then vertically would be that the system is coupled at one tier to a complex system of one of its constituents, right? And so there could be feedback between connectedness, coupling between those different tiers of organization, complex systems occupying either one of those tiers. So an example of horizontal connectedness might be something like the land-sea interface. So there are complex ecosystems on land that are undergoing various kinds of processes, biological and abiotic. And then another complex system might be the adjoining marine environment. So the top right-hand corner is the place that I ran every morning. It's a monarch reserve in Santa Barbara, California, and I go out there running each morning at low tide. It's a very nice, posh life. Anyway, so a lot of people are wondering why it is that kelp forests were vanishing and changing in composition in Southern California for a long time. Kelp forests are giant brown algae forests that are famous for having like seals and white sharks, and they're abundant from anywhere from, or they have been historically, from Baja, California up to the Aleutian Islands in Alaska. All of the western coast of Canada has can have kelp forests in it, and the species of kelp change across that space. But let's say you were interested in why it is that the kelp forests are changing in composition and dynamics in Santa Barbara, California. Well, the reality is that system doesn't actually exist in isolation, right? What's happening in a kelp forest is tied to other systems, other complex systems at its boundaries, physical or conceptual. So for instance, whether or not a fire is occurring and the severity of the fires that are occurring in terrestrial habitats adjoining the ocean will change things like nutrient influx that comes into that kelp forest, which in turn will change its dynamics. So maybe one of the reasons that you can't predict what's going on with the kelp forest, why it has one stable state versus another, or why it's transitioning between them, has nothing to do with something that's endogenous from that system itself, from within it, from its own normal feedback loops, but because those feedbacks are altered based on things like nutrient input from the terrestrial adjoining environment. There are tons and tons of little streams and rivers and type things. They're mostly streams. You wouldn't call it a river, but they call it a river, but they can be a dry river bed for much of the year. So anyway, little streams, tributary type scenarios that when there are fires, and then this rain immediately afterward will shut a huge amount of inorganic nutrients into those kelp forests, which will in turn change their behavior. So only by understanding both systems and how they work, and by what currencies they influence each other's collective dynamics, can we begin to infer either system's behavior. So connectedness can be in one direction, stuff happens on the land and it goes into the water, or it could happen in the opposing direction. For instance, what's happening on beach ecosystems, the sandy scorn beach here, might be contingent on both what's happening on the land interface, so the terrestrial zones more inland, as well as things like rack, i.e. dead plant material that's washed up from the kelp forests, right? So this intermediate interstitial space, these sandy beaches, might get influxes from both complex systems adjoining it. And in fact, for a variety of reasons, you might consider the sandy beach itself a complex system, although it's not a very speciose habitat. Anyway, connectedness in land and sea is an example of horizontal connectedness. Two comparable tiers of organization, both occurring at an ecosystem level, but they influence each other's collective behavior by basically exchanging nutrients and physical forces between the two environments. Horizontal connectedness can also occur in things like socioecological feedback loops in Moorea, French Polynesia. So, maybe you're interested in why it is that these fringing reefs are changing in composition from a coral-dominated system to an algae-dominated system in French Polynesia, the island of Moorea, which was an inspiration for Moana. They actually ended up interviewing a bunch of people that I know on Moorea to be the various characters. It's kind of weird for me to watch Moana because some of those characters are fashioned after people that I interact with or used to interact with semi-professionally. Anyway, that's beside the point. Anyway, so maybe you're interested in why it is that these fringing reefs here are beginning to become less coral-dominated. And so you're trying to figure out, why is it about the waves that are crashing over these reef crests? Is there something about the forereef, the coral reef that occurs on the oceanic side of that slope? That's changing, that in turn is impacting this fringing reef that's closer to shore. On the opposing side of the reef crest that's wave protected, is it something about the nutrient inputs from the pelagic zone? Is it a lack of propagules of corals that are moving across that environment? Or maybe it has nothing to do with the reef itself, but it has to do with things like social forces or economic forces on the fisher people, I should say, that that occupy that same environment, right? So it has nothing to do with the reef on its own, but how the reef is interacting with things like the economics of subsistence fisher people who are basically capturing food for their own survival, commercial fisher people who are catching food and then selling it to tourists as, you know, white or red tuna, or to natives to the island, or lastly, is it commercial fishermen that are that are coming in from for recreation and sport, that are coming in and changing those dynamics. Well, all of those interactors, subsistence fishermen, local commerce sort of fisher people, and then, or is it sport fishermen, and or their interaction competing with each other that is changing how they're exploiting the fish resources on the reef, which is in turn influencing the coral. Who knows? But they've been able to show over and over and over again that studying each of these things in isolation is insufficient, that you have to consider the connectedness between what's happening on the island, what's happening beyond the reef crest in the pelagic zone, what's happening in the fringing reef itself, and what's happening to the human users that for economic, cultural, and business purposes need to leverage the resources that are coming out of these reefs. And so not only do you have to know how these things are coupled together, what's happening in each of them to understand the aggregated outcome for these reefs, but you have to manage them with all of these competing concerns in mind, right? And so connectedness is an important feature about complex systems, because when it's present, it means that in order to understand the collective outcome understand the behavior of any one complex system, you have to be able to infer what's going on in other systems and how are they related to each other, how are they linked. Vertical connectedness is just up and down tiers of biological and abiotic organization. So the brain, a heart, a liver, a circulatory system, these are all complex systems that have various sorts of features about them and their own internal dynamics, but they are also all combining together and reacting to each other to determine what's happening at the individual behavior or individual's physiological state or morphological state, like a whole mongoose. This is a meerkat, which is a kind of small social mongoose. But then that individual state, let's say behavioral state, is not only contingent on the feedback between the organ systems within that individual, but is also contingent on its recent behavioral interactions and its social position in its social group. But then how those social groups interact with each other and will also influence at the next tier biological organization, like the water retention times at an ecosystem level in the Namib Desert. When there are tons and tons and tons of soil disturbances by these meerkat, that will change things like water retention times and the ability for plants to be able to persist or germinate in such an arid environment. And then, but it can go up and down tiers of organization, right? Obviously, whether or not water is retained in soil for a long time or a short period of time, and the amount of vegetation will change things like structural integrity of the tunnel systems of these social groups. And that in turn will change things like the individual behavioral states and stress physiology of the constituents of the group. And in turn change things about the probability of brains and livers and hearts and whatever systems at a sub-individual level from occupying one kind of stable state versus another. Is this useful for a scientist to know? Well, if you're trying to predict the complex behavior of any of these tiers of complex systems, it suggests that you need to basically cross normal interdisciplinary bounds until you figure out what the important inputs are to your focal complex system, and the least numerous other complex systems you have to attend to figure out or predict the behavior of your focal complex system. So it's all well and good to say that everything's connected to everything, and so it's so endlessly complex, we're never going to understand it all. That's not the take-home message. The take-home message is basically like, your complex system is probably going to be importantly linked to one or a few other complex systems that once you acknowledge these small number of important levels of connectedness, you'll be able to understand the aggregated multi-system, meta-system more effectively. But also along those lines, it's important to know which systems are not importantly connected to each other, so you can begin to triage things that are superfluous to your goals and only attend to the things that appear to actually be important. connectedness. The parameters of one system, i.e. the x-axis on those nonlinear figures that we've seen before and we'll see again, are oftentimes changed by the state of other systems. So another system is doing something different, and that will feed into the parameters of your focal system. So things like ash retention time in the terrestrial environment on the coast of Santa Barbara is something about its state. But that state is going to change things like nutrient input to your kelp forest, which might be your x-axis when you're thinking about your kelp forest. Oh, you know, what's going on with these nutrients and how is it changing the sort of stable community composition of my kelp forest? But in order for you to even understand why it is that X is fluctuating on your kelp forest figures in your mind, how you conceptualize it, you need to understand that that system is importantly linked to things like the inorganic molecules that come from terrestrial environments nearby and fire. And predicting those will be contingent on trying to figure out why it is there's high or low ash retention time in post-fire environments along the coastline. Tipping points and hysteresis. I have a sip of water. Tipping points. So we've already mentioned previously that feedback loops and feedback of various kinds cause the system to stay in one state versus another. Oftentimes these properties are depicted using something like a soup bowl type figure. The idea is that your system, say it's a social group or an ecosystem or whatever, has a current state that it tends to stay in. And if you have small perturbations, like just by chance alone, it wiggles around and becomes, you know, drifts away from its normal states in a subtle way, it tends to revert back to its normal set of conditions. So if you perturb it, it tends to go back to its current set of conditions. And you can imagine this being like a little ball in a bowl. And although the ball might jiggle back and forth because of fluctuation across days or minutes or years or whatever, it tends to remain in the same bowl because even though it jiggles around, it tends to roll back to that exact same spot. And the reason that that is because under most conditions, in most circumstances, there are negative feedbacks that are stronger than the force of positive feedbacks. Positive feedbacks usually cause systems to revert between states, cause accelerating change, like, you know, that nonlinear graph of population growth, the accelerating component, and then negative feedback loops tend to keep things where they are. So the idea here is that although the system could jiggle in one direction or the other, the negative feedback loop, the reduction in the system's tendency to move beyond that point is greater than any sort of positive feedback loop that would cause that small change to crescendo and create more and more change in that direction. Now, these hills are places where the system is much less stable, right? So if there's a large perturbation in the system and it reaches past this moment, there's a chance that a positive feedback loop could cause it to move from one stable state or to another. If the perturbation is small enough, it should roll back to its previous set of conditions. If it reaches some threshold, though, of perturbation, then a new set of dynamics, a new set of feedbacks can cause it to transition into another state. These sorts of graphical wells are called basins of attraction, which are just the set of points in a graph of the state of a system where even though you perturb it, it reverts back to its former set of conditions. So even though some years there might be storms that cause 10% or 20% of the kelp fronds to be removed because of physical perturbation, the system will tend to revert back to its normal set of density of kelp. So that would be an example where, although there are perturbations, the kelp forest reverts back to its normal set of conditions. Urchins come around, mow down a bunch of kelp fronds, but because it's happening at such a low rate, all of the fronds basically will replenish back to the normal set of conditions, set of densities through time. However, if the perturbation is large enough, then maybe say 50% or 80% of the kelp forest fronds are removed from storms or from herbivory, from urchins. Well, suddenly the urchins that are there might be so hungry that they can eat all of the remaining kelp fronds. In which case, you have broken down the feedback loop that kept that kelp forest in its current state. The ability for local kelp to replace themselves was that feedback that kept that system in its current state. And then if you perturbed it, it could regrow itself back to that normal state, that normal density of fronds. But if you perturb it enormously, then you can cause that feedback of local fronds causing new recruits of younger fronds that in turn replace them to break down, which means then you can go things like an urchin barren state where there's very little or few kelp that persist, and the ones that show up are quickly mowed down by urchins. It's a classic ecological example. All right, urchins eat kelp, also heads up. Well, the urchins can eat lots of things, but they can eat kelp. All right, so small perturbations cause the system to return back to its normal state because of negative feedback, but then if you reach a certain threshold, then a positive feedback loop can cause the system to continue to change and enter a new stable state. Most environments that we see right now, most social groups, most individual states, your current brain chemistry state is at a stable state. It got there probably by passing through one of these key moments where it went from one behavioral state into another. And then there are feedback loops that keep it there. Think about it like human emotions, right? If you're in a bad mood, you tend to see other bad things, or you tend to interpret other sorts of things as in a negative light. That tends to keep you in a sort of a negative mood. And somebody who's in a very positive mood can go through, can just basically paint all of their life with rose-tinted glasses and see things in a strictly positive light. That tends to keep their brain in that state. And then occasionally there's a bad enough perturbation, something so bad or so good happens to you that you transition between those stable states. And now, although you're normally a very happy person, you can get a sort of a negative train of thought. And vice versa, right? Even though somebody's a sourpuss all day long, totally acrimonious, something good enough can happen to them that they start to just see things in a more positive light for a little while in time. You can depict that sort of tendency to remain in one train of thought or another as a set of attractor states in a complex system like your brain, right? That has feedback loops that tend to keep it in one state versus another, right? But the depth of those basins of attraction probably vary between individuals, right? If you're somebody who has a hard time just seeing everything in a really rosy way, let's imagine the left-hand side here is sort of a negative or highly critical train of thought state, and the right-hand side might be like a very positive sort of train of thought mental state. Well, if you're a positive person, it's probably because of both developmental and genetic reasons that your basin of attraction for your positive state is steeper, right? And probably wider. So perturbation, something bad happens to you, although it shifts your mood a little bit, it will tend to revert back to your normal mood. And if you have something that's really wonderful that happens to you, even though you're a positive person, you can only feel so wonderful for so long, and then you tend to drift back to your normal mental state. Conversely, individuals that tend to be more critical, self-critical, or critical beyond themselves might have a deeper or wider basis of attraction around a mental train of thought that keeps them thinking about things in sort of negative or critical lights. Oftentimes, negative and critical are used interchangeably, but oftentimes people have incredibly adept perceptions of reality. Being somewhat of a glass half full type person oftentimes result in you making accurate predictions about your environment. This sort of attractor state and mood case study or model that I've tossed out here, which I didn't intend to talk about, is exemplified by things like winning the lottery. All right, you win the lottery today. You didn't realize you bought a ticket. You win the lottery. Guess what? For a little while, you're just going to be so excited. Hooray. But the reality is you're still the same person, right? So most studies show that you only have an elevated sense of happiness for maybe like 3 to 6 months after a really wonderful thing happening to you, and then you go back to your normal level of happiness. And if that's not that happy, well, that's just back where you are. And conversely, if that's extraordinarily happy, then you just go back to that normal level of pretty extraordinary happy, but not endlessly, enthusiastically, both feet are off planet Earth levels of happiness. All right, and conversely, let's imagine that you are framed for a crime and you go to jail. You didn't actually do it. You could be really upset, right? That could negatively impact your emotional state. But you're only going to be sad for so long. And then even when you're in jail, you're going to revert back to your normal, oftentimes genetically influenced level of happiness. I mean, there are prescriptive things that you can do in terms of training your mind. There's developmental influences, but there is actually a genetic influence on your level of happiness you're likely to perceive for the rest of your life. You can change it. You can change the shape of those basins of attraction, but you have those basins of attraction and they are powerful. So even wonderful or horrible things that happen to you, your mind will tend to slide back into its normal state of emotions, train of thought. I hope that was a kind of fun psychological example, but I being an ecologist myself, I'm going to use a lot of ecological examples. So what is a tipping point? A tipping point is basically that moment when the parameters around a system, the environmental features, cause the very shape of these basins to change. So there are attractor states, and they're around all over the place, but they don't just stay where they are. There are environmental features that, as they change, the feedback loops that make these basins of attraction stick around can slide around themselves. So, for example, if you change something like the external conditions, I call them parameters, but some in bottles call them conditions. If you change the parameters, external parameters around a social group, you might find under some sets of conditions, a social group can be like in this intermediate portion here, in a ticked off aggressive state or in a docile state. But if you change the conditions, like say, we're going to say the left-hand side is docile, the right-hand side is aggressive. If you deplete the food enough, then a social group might reach a state where the only base of an attraction for it is endlessly high levels of aggression, right? So under very food limited conditions, there's only one attractor state, and that is in a social group of only being aggressive towards each other. If you started to ratchet up the amount of food moving down this axis into the left-hand side here, you can see that at some level of food, even though there's a primary attractor state where the social group is mostly aggressive, that still could be in a docile state. But as you add more and more food, the docile state becomes more and more stable and easier to attain. And there's a huge level of food, then basically no one's being aggressive towards each other. And the only basis of attraction that exists is a docile state for the social group where everyone's getting along. So food from the top right-hand corner being very limited, only one basin of attraction. A lot of sets of conditions that allow multiple different basins of attraction, right? There are two different stable states that a social group can occupy. Kind of angry with each other, kind of nice to each other. And then under a high level of food, we can see that we again are in a single basin of attraction set of conditions, but now the only basin of attraction is around the docile state. What goes on that axis here for conditions? Parameters can be things like heat, precipitation, nutrients, food availability, whatever the important conditions or parameters are for your system, that's what's going to tend to go on that axis there. And the reality is, no surprise that those basins of attraction can change if you just change the parameters surrounding your complex system. The fact that that is possible means that if you transition into one of these states because of environmental features beyond the group, the parameters, then if you're trying to maintain a group in one state, like say you only want to have docile social groups, well, if we fish the food that these things eat, or we exploit them as a human society down to a critical level, well, then you won't be able to preserve that docile state any longer because the very feedback loops that could cause it to be, to develop and to persist are gone. They've broken down because the external environment has changed so drastically that the very kinds of feedback loops that determine the states that are available to a social group can change in response to these shifting parameters. All right, a lot of words. Here's an example, near and dear to me, where we're talking about, again, these aggressiveness in a social group. And so now we have temperature along the x-axis here, which is our environmental condition or environmental parameter. The y-axis here is the level of aggression within that social group. So at very, very cold conditions, the only set of conditions are groups of spiders that are being nice to each other that tend to be docile. At intermediate conditions, you can have a social group that can either be very aggressive towards each other, or the group could be social and docile towards each other. And the probability of being in either one of those states is contingent on where it was before. In B or C, the ball that's in the social group that's in a docile state tends to remain in a docile state even with small perturbations. In C, the same thing is true. In D, the same thing is true. However, the degree to which that basin of attraction for that docile state is sharp and reliable gets shallower and shallower as you get to hotter conditions. Why? Because even a nice group of spiders that are being nice to each other, if you ramp up the temperature hot enough, then they will start to get ticked off and aggressive with each other. And soon you can reach a critical level of temperature where the social group is forced to be only aggressive to each other. There is no such thing as a docile state. But if you begin to cool that social group down, they're in a ticked off state that tends to remain there, right? So even though there is in B, C, and D, there is a state where the social group could be placid, the ball that started off in the aggressive state in E, when you're cooling that group down, is going to tend to stay in that basin until it reaches a threshold, a tipping point, where the basin of attraction for the aggressive state becomes so shallow that the ball, just by random chance, falls into this other basin of attraction for being docile. What this means is that whether a social group at a temperature like C is aggressive, the red ball, or docile towards each other, the blue ball, is determined based on where it was to begin with. If the ball was near the basin of attraction for a docile state in C, then it will tend to remain there. But if the ball had been in the red basin of attraction, it will tend to remain there, which means that at an equivalent temperature, a social group could either be stably aggressive or stably docile, all depending on its history. If the group was previously very hot, it will tend to stay in that hot, aggressive basin of attraction until that basin of attraction is gone. The group has been cooled down so much that the group becomes docile once more. And then once it's been docile, it doesn't flip so easily back to being aggressive unless the temperature really heats up. So for lots of intermediate temperatures, you can have the group at either one state or another, and which one it occupies depends on its history, and small perturbations will result in the social group staying in its current state. Large perturbations, especially ones that change the shape of those basins of attractions, can cause tipping points, which result in the group shifting between states. And the fact that there's this reliance on this group's history to predict its current state, that is called hysteresis. So due to feedback loops and inequalities and those changing, so feedback loops cause basins of attraction. Shifts in the environmental conditions or parameters around your complex system can cause the shapes of those basins of attraction to change. That is called a tipping point. The fact that there are that the behavior of a system, whether it stays aggressive or docile, is contingent on its history, where docile groups tend to remain docile until they're really heated up, and aggressive groups tend to be aggressive until they're really cooled down, is called hysteresis. The state of a system depends on its past. That's the definition. And by the way, the feedback loops that keep a group in an aggressive state is because aggressive groups are fighting with each other all the time, and that tends to cause more aggressive behavior in other group members, i.e. a positive feedback loop of aggression in a social group tends to keep them at that high aggressive state until you cool them down so much that they just can't be ticked off at each other any longer, and they all have to sit still because they're ectotherms. And then even though when you warm up the group, although they could be in a heightened level of aggression, they don't have that positive feedback loop from their history, their recent history, to keep them in that state. So instead, they tend to remain docile until you heat them up enough that just individuals start bustling around and fighting with each other, and then that keeps them back in that positive feedback loop that keeps them in that aggressive state until you cool them down again. This is called a hysteresis loop. So at an equivalent temperature or set of environmental parameters, there can be two different states or more states that a group can occupy depending on their history. Hysteresis. So a non-behavioral example might be something like whether or not you have a true desert or an arid grassland. And there's an amount of precipitation that can cause an arid environment that's a desert to enter an arid grassland state. We'll just call it a grassland henceforth, desert, grassland, although they're the exact same plot of land. You know, a grassland, if you choke it off of enough water, will become a desert. If you give deserts enough water, they'll become a grassland. All right, no surprise. But there are lots of conditions of intermediate levels of precipitation where a system can either be a desert or a grassland. Why is that? Well, most ecologists would just say, there's a relationship between a precipitation and whether you're a desert or a grassland, and it's strictly deterministic. It has nothing to do with the history of the system. You reach this key moment, a grassland just becomes a desert. There are no sets of intermediate conditions of precipitation where the system can occupy either state. That's incorrect. Grasslands tend to be sticky and stay a grassland in this in these graphical spaces, because when it rains, the rain doesn't pass through the soil so fast. It wicks around patches of grass and trees, and then the water more slowly goes through soil in those areas. So tufts of grass and pre-existing plants cause water to sift through the soil more slowly. And that means that it's available for things like seeds for longer so that they can germinate and make more grass. Grass makes more grass, not only because they have seeds that they're producing that are recruited to the seed bank, but also because the grasses themselves slow the rate with which water goes through the system, which means that it's accessible for longer for new grasses. However, there's some low level of precipitation, a high level of aridity, where all those grasses are going to die. And soon they'll just sort of like weather away and it'll be completely dry. The grasslands can't persist. Some extraordinarily high level of aridity, akin to that aggressive spider group. However, when the rain starts back up, it doesn't immediately transition back to where it's a grassland again at the exact same moment in time. Arid environments tend to stay arid because when the rains do come, the water passes through the soil so fast that the seeds can't really use it for long enough to germinate, right? Or young plants can't get enough of it to grow, and mature plants don't get enough of it to reproduce. So at an equivalent level of water, precipitation, the same patch could be a desert and stay that way, usually, mostly, or a grassland and tend to stay that way, all contingent on its past. If there's already pre-existing grass there, the system's going to tend to stay in that state because the grass keeps the water around for longer for more grass. If it's been in an arid state, then all those plants are dead and that water passes through more quickly, and so new plants can't get access to it. So trying to preserve something like a grassland when an area becomes incredibly arid becomes challenging, because even when the water comes back, the system doesn't go back to its previous state. It doesn't just switch back to a grassland overnight. It takes a huge amount of water before it can get back to that state, because the water that does show up can't stick around. Pre-existing plants capture the water around. So things like conservation can't function so effectively under such circumstances because they'll be mystified. We added more water and it didn't go back to being a grassland. And that's because there are things like positive feedback loops inside of these habitats, like grasslands, that break down when the system becomes too arid for too long. And when those break down, that means that stable state is not present. In order for you to recover it again, that basin of attraction, you have to make the system much wetter than it was when it transitioned from being a grassland into an arid environment. So that again is hysteresis and would cause a hysteresis loop. So tipping points, spooky, right? They're spooky because they're hard to predict. You don't know what a system's going to do when it's entering novel sets of parameters, novel sets of environmental conditions that could change the kinds of feedback loops that a system is experiencing, and in turn, what kind of states it can be in, the shape of those basins of attraction, and how the complex system behaves in aggregate. So a lot of attention has been paid to thinking about, are there early warning signs about tipping points? Are we going to be able to tell that one is forthcoming and be able to intervene, or are we just going to be mystified when it happens and that the system's entire dynamics are going to change and we're not going to be able to figure out what happened really? Well, you hope, let's all hope, that there are warning signs, and indeed there are, right? So tipping points, there's spooky, like this spooky house on the right-hand side. Can we forecast them? Well, it seems like it's important. The environmental parameters of all of Earth are changing all the time. It would be really nice to know where those tipping points are in environmental space and be able to make sure that whatever systems we like on planet Earth, our own societies, important ecosystems, fish populations that we cultivate, timber populations that we're trying to leverage through the years, we'll have to be able to know when they have a risk of passing through a tipping point and hopefully avoid them from passing through those tipping points. So if you just measure the system state through time, so these are those basins of attraction pictures. So on the left-hand side would be a system that has very, very deep basins of attraction that are very strong. To the right would be a system that's very close to a tipping point, right? So the basin of attraction on the left-hand side is actually pretty shallow. So just chance alone could cause this system to go back and forth and enter a new set of dynamics that cause it to go to this much deeper and more stable alternative state over to the right, which might not be very desirable. So if you just measure, all systems jiggle around a little bit in their behavior through time, just by chance alone. So the ball jiggles back and forth on its own. Such random perturbations in a base of an attraction, like on the left-hand side, result in the system swiftly going back to its normal set of conditions. That means that it's not near a tipping point. Its current feedbacks that's keeping it in that state are strong enough that it tends to remain in its current state. However, as the environmental features around it change and the severity of that basin of attraction changes, then we can reach a state where when we perturb the system, yeah, it goes back to its former state, but it takes a long time to do it. The ball rolls more gently because those feedback loops that are keeping it in that state are weakened. They've degenerated. On the left-hand side, they're completely intact. You're nowhere near a tipping point. Those basins of attraction still look very sturdy. Right-hand side, basins of attraction, at least the left-hand side, has weakened, and so it takes longer for the system to recover, and then those little perturbations on their own mean that the system's gonna have larger sweeps back and forth because those feedback loops keeping it there, they're not that strong. If the feedback loops are strong, then all those perturbations are gonna have very little impact on the system's state. So left-hand side, if you're just plotting the state through time, those little jiggles of the ball cause very little change in the system's state. The same equivalent amounts of jiggling when the bases of attraction are shallow cause huge swings compared to the left-hand side, huge swings in system state. And although it tends to recover to its baseline, it takes longer to do it and it's noisier when it does. So increased variance in the system as we change things like pollution inputs or the amount that we're fishing or the, or the amount of precipitation in a given environment, we can begin to see that the variance in the system, although it has the same mean, is going up and up and up. And that means that that basin of attraction appears to be breaking down. The system's, the kinds of features about that system, the dynamics that keep it in its current state are going away or weakening. And there will probably be a moment when they no longer exist, they break down entirely, and the system enters a new qualitative state, this right-hand basin of attraction. Critical slowing is that recovery time. So if you perturb the system on the left-hand side, like in C, it has a stable state along this red line, but there's a perturbation, a big one. The system quickly goes back, short time interval on the x-axis, back to its normal state. If that basin of attraction is breaking down, then an equivalent perturbation, yes, eventually goes back to its original state, but it takes a long time to get there, folks. And the fact that it's taking so long to return back to its former state means that those feedback loops are breaking down. Those basins of attraction that they create are becoming shallower and more opaque. So if we're monitoring things like imperiled lakes or fish populations, and we begin to see that those states are becoming really noisy, and then when they have a year with really low fish availability, they recover really slowly through time. That means that the basin of attraction is not that strong, it is weakening. And that's it. I burped in your face the last minute. I apologize for that. I always eat right before I give this lecture, and then it's a mistake because I'm having like hiccups the whole time in front of you. I'm sorry that I'm gross. Oh yeah, that's right. One other thing, more important than me being gross, is that on Wednesday, during our normal class time, I'm going to have a review session for the exam. So I'll post this lecture, the last lecture on complexity theory, in the morning. During our regular scheduled class time, which I think is 4:30 on Wednesday, I will have a Zoom impromptu office hours discussion section where people can ask me questions on any of the topics on this exam, or the last exam if you want, but hopefully this exam. And so during our regular scheduled class time on Wednesday, I'll be doing a Zoom question and answer session. So just before the exam, so that you can, I don't know, feel reassured if you've done the studying and begin to map out what's important if you haven't started to study at all. I know a lot of you are going to be binging these videos the last minute. Although you shouldn't do that, it's bad for you. I'm also not going to judge you because, like, whatever, it's the exact same thing I would have done when I was an undergraduate. There's a lot of other stuff you could be doing, and I am less interesting than some episodes of Netflix. I hope I'm somewhat more interesting than some things on Netflix and YouTube. I fell intermediately. I cannot be the most boring thing online. Anyway, how did I get on this topic? You tricked me. Anyway, take it easy, guys. I will see you guys Wednesday. Have a good one. Bye.